And then we're going to continue with the problem set that we started on Friday. So I did send that out on Canvas on Friday. So you might want to pull up that PowerPoint just so you have the problems written out already. It'll save you a little bit of time. Okay, how was everyone's weekend?
Good.
It was good.
Awesome.
And you?
How was yours?
Oh, mine was fine. Yeah, Halloween was a little not what I was looking forward to since last year, but that's okay.
Wait, what happened last year? If you don't mind me asking.
Oh, no, I just love spooky season. And my friends and I usually have a really good time, like doing spooky things all month. And so, you know, this year, just not really being able to hang out with each other was kind of a bummer.
I feel that.
I did, I recorded a video for you guys I'm going to send you. I carved a pumpkin and then set it on fire using chemistry. So I'll send that out to you guys later today. I forgot to send it out over the weekend.
So what was the question thing called again? Sorry.
It was in an announcement that I sent out to you guys. That's probably the easiest way to find it. It just says like today's PowerPoint. It was sent on Friday. So if you go under the announcements, you'll be able to pull it up pretty easily.
Yeah.
I'm seeing a lot of sadness from football fans. My family is a Saints family, so we were pretty happy. Okay. So on Friday, we did the first 3 slides. We're going to go through the last of these problems. These problems kind of cover the big ideas from chapter 18. And then if we manage to get through all of these, we'll start talking about aldol condensation. So did anybody take the time to look at these over the weekend and think about it? I see a little bit of yes action in the chat. I love that. That's awesome. Okay, so when you look at this type of problem, this is kind of a synthesis action here. And I see a lot of no life happened over the weekend. I definitely get that. Okay, so this is kind of a synthesis problem. It doesn't have that many steps, so it's not too bad. We do need to add on a couple carbons, right? We have a main framework of 1, 2, 3. This is a malonic ester. And then we have that same framework here. The reason that we know that these are the same carbons is because we have these oxygens attached. It's not really possible to take this area and turn it into something like that. So having these 2 oxygens on these carbons gives us a pretty good hint that we're looking at these groups getting turned into alcohols. So then the only other thing that we need to figure out is how am I going to make a bond to an ethyl group, right? So what do we need to do first? Can we turn the ester into the alcohol first, or do we need to add the ethyl group first?
Add the ethyl group.
Right. So yeah, I see some suggestions in the chat. We need to add in a strong base. So what would be a good strong base for this? Yeah, we could use LDA. That would definitely get it done. I see Warren is suggesting ethoxide. That would also work. Because remember, the pKa of this is pretty low. So ethoxide would be probably efficient enough. LDA would definitely get you 100% deprotonation. So that's always kind of a safe bet. So if we add in LDA, we know that we're going to pull off the alpha proton. And we're going to end up with an enolate. Remember, the great thing about this enolate is that it has 2 resonance forms, right? We can push the electron density onto this oxygen or this oxygen, and we can even put in some electron density from our ethoxy oxygens, although those are not major contributing structures. But that's why we're able to make this enolate so easily. So then we want to add on our ethyl group. What do we need to add in?
Would it just be like an ethyl group attached to a bromine?
Yeah, you could do ethyl bromide, ethyl iodide, your favorite halogen, just not fluorine. You could also have done this as a step 1, step 2 situation if you want, but I wanted to draw out the enolate and talk about it. So then from here, we've done an SN2 reaction and added on 2 carbons. Okay, so then how can we turn esters into primary alcohols?
Use a strong reducing. Strong acid and heat.
So I heard strong reducing agent. If we use a strong acid and heat, we'll end up with a carboxylic acid, and we'll also end up decarboxylating. So we don't want to risk that here. I see a lot of strong reducing agent being suggested in the chat. Oh yeah, so Warren and Allison both suggested lithium aluminum hydride. That's exactly what we want. Sorry, I'll leave the chat open from here on out so I can read it more quickly. So if we do lithium aluminum hydride and follow it up with an aqueous acid workup, we will be right on track. Okay, does this make sense?
Would you just say that, like, because I mean the product looks a little bit like rearranged differently. Would you just like knock it up to that it's just rearranged differently?
Yeah, so all it did was take this structure and rotate it a little bit to the side so that, you know, the ethyl group is down here. We could have drawn this structure to kind of look like our product as well. Let's see. So that's all. It's just a rotation.
All right, thank you.
Mm-hmm. Yeah, and that's a really common tactic in this chapter. Unfortunately, like when I give you guys questions like this, I'm not trying to trick you. I'm not trying to mess with you. It's just trying to make sure that you're actually thinking about where the carbons are coming from and not just like on autopilot. You're actually more likely to make mistakes if you go onto autopilot. But if you're actually, you know, double checking your carbon count and thinking about where these carbons are coming from, you're more likely to get it correct. So you'll see in your homework that sometimes they rotate the problem, and I'll do that in your quizzes and exams as well. Okay, this one is obviously not a synthesis, it's just a series of reactions. So we just need to go through this step by step and try and you know, figure out what our final product is going to be. So what is happening in step 1?
Is it the ethoxide from the NaOET is attacking the alpha hydrogen?
Right, we are going to deprotonate using ethoxide, which is what was suggested on the last page, and it would work because that proton is pretty acidic. What's the pKa of a proton on a malonic ester?
Is this the 12.9 one?
Yeah, this one was around 12.9. And then our other product would be ethanol. What's the pKa of that? Yeah, so Wesley got it in the chat. It's close to 16. So remember, alcohols are very similar to water as far as their structure, and their pK is very similar as well. Your average alcohol tends to be between 16 and 18. And the closer it looks to water, like the smaller the carbon group, the closer it is to 16. Remember, the pK of water is 15.9. Okay, so then we have our enolate. The ethanol is not something we're going to use in the reaction. What happens with the enolate and this? What is this compound?
Is it an epoxide?
Yeah, it's an epoxide, and it's called ethylene oxide. Allison requested a list of all the pKa's you need to know. Yes, I actually started the list and I didn't finish it.
Would the
not helpful.
would the carbon on the epoxide attach to the negative charge and then open up the ring?
Right. So the enolate is going to attack one of the carbons here. It doesn't matter which one because it's symmetrical. And we're just going to bust it open and put the electrons onto the oxygen. So then that means in step 2, we have this. Okay. And then in step 3, we're adding in H3O plus and heat. This step is kind of tricky. This is another really common thing that you see. I actually pulled this from the old textbook. It was a synthesis problem, and instead I wrote out the steps because this step can be kind of tricky. So what's one of the big ideas that's going to happen first if we add in aqueous acid?
Protonation?
Would it turn the esters into carboxylic acids?
Yeah, so I think both things were listed just now. We're going to turn the esters into carboxylic acids, and we're also going to protonate that alkoxide we just made. What is the heat going to cause, though? We're not quite at our product for step 3 yet.
Decarboxylation? Should there be 2 carbons on the way that?
Oh, yes, I'm sorry. Thank you. Yeah, I'm always getting on to you guys to count your carbons. That's why. Okay, so yes, I don't remember who said it just now, but we are going to decarboxylate. That's what the heat is going to cause. So after step 3, what we actually have is a carboxylic acid, and then we have 1, 2, 3 more carbons. 1, 2, 3. Let's double check. 1, 2, 3, 4 total. 1, 2, 3, 4 total. Okay. I shouldn't have numbered 1, 2, 3. That's obnoxious. Okay. So then we have lithium aluminum hydride followed by aqueous acid. These can go together. What is that going to accomplish?
Turn the carboxylic acid into a primary alcohol?
Right. So we're going to end up with a 4-carbon diol. So what I really like about this question is a lot of times when people see, draw a synthesis from here to here, the main mistake that's made is this is 1, 2, 3 carbons. This is 1, 2, 3, 4. People don't catch that and they just reduce the esters and think that they're done. So it's really important to count your carbons between your starting material and your product, as well as while you're drawing your products. Okay, any questions about this page? Kind of a fun problem. I really love these last several chapters of OCHEM. I just think they're so great. Okay, so this is acetoacetic ester. This is another major topic in chapter 18. Let's go ahead and do just a little bit of analysis here. In our product, we end up with 1, 2, 3, 4, 5 carbons. In our starting material, we have 1, 2, 3, 4. Do you think that this carbon 4 is the same as this carbon 4?
No.
Yeah, probably not. So we can go ahead and kind of assume that what's going to happen to carbon 4.
Decarboxylation.
Right, we're going to end up decarboxylating. So that means that we want to add on carbons 4 and 5 ourselves. And so this is going to look a lot like another problem we've already done. Okay, so what do we need to do first?
Tackle the PTO.
Oh, sorry, accidentally. Yeah, so we need to deprotonate. So we can add in sodium ethoxide again, or we can add in LDA. Let's go with ethoxide this time.
How do you know which one you should use?
In your videos, you mentioned using like a whatever like pulls off the alpha hydrogen that's similar to like the ethoxide. So like you use the ethoxide because it had ethoxide on it.
So that really only matters for the Claisen condensation at the top of chapter 19. You would not want to use like methoxide because you might end up changing out your ester. In this case, it doesn't matter because we're not carrying over our ester to our product. So you could kind of use whatever you wanted here. And then I think somebody else asked, how do you know which one to use? It's just a pKa game. If ethoxide is strong enough to deprotonate, then you can use ethoxide. If it's not, you need to use LDA. So I guess one of the ways you can interpret that is LDA is never wrong if you're doing a synthesis.
Is it because the pKa difference is so much with LDA versus?
Yes. Yeah.
Oh, you're
right. So Allison is asking what's the cutoff for pKa strength in order to use it. With acetoacetic ester and malonic esters, you're always okay to use ethoxide. Anything else, I probably wouldn't. I would probably use something else. So for dicarbonyl compounds, you're good to use ethoxide. But if it's a single carbonyl, you need to use LDA. Okay, so after we add in ethoxide, we've deprotonated our alpha hydrogen. And I'm sure we're starting to notice this is super repetitive, right? OChem is very repetitive. What do we need to do next?
Attach the ethyl group to like a bromine or chlorine or something.
Yeah. Yeah, Warren, you're right. Ethyl bromide is good. Rachel. Okay, so this is going to take out the bromine. Okay, and then how do we get from here to here? We only need one step.
H3O plus
heat.
Aqueous acid workup and heat. So the aqueous acid is going to get us to the carboxylic acid. The heat is going to get us to decarboxylate. So then we have 1, 2, 3, 4, 5. That's our carbon assignments in our product. This is a pretty common acetoacetic ester problem. Any questions on this page? That was somewhere in between the last 2 problems that we worked. Okay, this one's a little more challenging. So there's one carboxylic acid group here, and there's 2 carboxylic acid derivatives here. So what's one thing that we know is going to happen?
Decarboxylation.
Decarboxylation. So I'm just going to list things off over here.
And then we're changing one of the esters to a carboxylic acid. So the reduction.
Yeah, and we can always do, no, you don't have to reduce, you just have to hydrolyze. So we can do that all in one step for the decarboxylation. Is that going to be towards the beginning or towards the end?
Towards the end.
And
It's usually the last step if you're ending with a carboxylic acid. So we can actually, you know, go ahead and look at this as a backwards synthesis, if that might help us see what we need to do a little better. So here, we can go through a couple steps if you'd like. This would have come from a dicarboxylic acid. Right, this would get decarboxylated. We can also go ahead and just have the ester right here if you want, because it will get hydrolyzed. You're welcome to break that out into 2 steps. Let me show you what that would look like, because sometimes students prefer that.
Yes, please.
Yeah. Okay, so we would have gotten this from an ester because we started off with a diester. I don't know why I circled that so vehemently. Okay, so yeah, what I was saying is that you could also shortcut like that. Same thing so far. So we need to figure out how to get from our malonic ester to our malonic ester with a cyclic ring there. I'm going to show you real fast the most common mistake. This is the single most common mistake that I see. Why does this not work?
You'll have an extra carbon sticking off of it.
Yes, if you do this, you're going to end up with another bond to a cyclohexane ring, and that's not what we want, right? So what do we need to do instead?
You could put Br on both ends of pentane.
Yeah, so we could do, I'm going to put these all into one step just so we don't have to keep drawing out an anion. We need 1, 2, 3, 4 carbons in here. So 1, 2, 3, 4, Br. So when we do this, our next step is going to be, our next intermediate rather. 1, 2, 3, 4, Br. So then what could I do to displace that last bromine?
You could deprotonate another hydrogen with ethoxide.
Yeah, so there's still one more hydrogen here. Here is a situation where maybe using ethoxide is not the best because ethoxide can also be a nucleophile, but LDA will not be a nucleophile. So adding in LDA will get you to your cyclic thing here. You'll end up deprotonating and then attacking there to create a cyclic structure. Does anybody need the intermediate enolate? I can draw that out real fast. It doesn't take very long. So what we're getting on our way there. 1, 2, 3, oops, missed one. 1, 2, 3, 4, okay. Is this enolate, which will then attack, kick out the bromine. So yeah, this is another very, very common type of synthesis. Now that original thing that we did, you know, with the mistake, if you end up with something like this, then it is as simple as adding in bromocyclopentane, right? But since we don't have the extra carbon in between the carboxylic acid and the cyclopentane ring, we have to do an alkyl dihalide and create our cyclic structure ourselves. Okay, any questions on this? I love this chapter so much. I love chapters 18 and 19. Okay, so I will post that with the answers up on Canvas after this class period. Okay, are there any chapter 18 questions before I introduce some things for chapter 19? Okay. Okay, so last Monday, we're not going to go back over this entirely, but I do want to kind of just skim through.
Somebody asked you a question.
Okay, one second. Sorry, I'm trying to make sure I'm sharing the correct thing. Okay, where's the chat? Yes, Allison, that's actually exactly what we're about to go over. So your alpha hydrogen acidity, this is something that you need to kind of memorize. There are some ranges and approximations that if you have those in your head, you're good to go. Over the last quiz where I asked you for specific pKa's, or I said like approximate pKa, you could have answered anywhere between 9 and 11 for the diketone that I put there, and you would have gotten it correct. So I'm just looking for ranges here. And then for diethyl malonate, I did put in 12.9 as the correct answer, but then had some leeway of like 1 or something. So as long as you guessed somewhere around 13, you would get the answer correct. So for all of these, it's always approximate. As long as you know the general area of the pK, then you're good. These are the ones that you need to know for sure right now. So key factors to remember is that proximity to the aldehyde or ketone does matter. So your alpha proton is next to a ketone or an aldehyde is going to have a pK of about 19 to 20. And then once you get removed from the ketone here, you're really kind of back up closer to your alkane acidity. It's not very acidic at all. So your beta hydrogens have almost no acidity. So we're really only talking about the alpha hydrogens here. Never ever pull off the aldehydic proton. Ooh, oh, I forgot I drew that on here myself and I accidentally erased it. Okay.
Would that proton on the aldehyde be the least acidic then, right? Because we're not touching it?
Yes.
Sweet.
Yeah. On this molecule. And then pK for this one is about the same because it's just next to one carbonyl. Now, if it's next to one ester, like in this case, it's slightly less acidic at about 25 for an ester. Does anybody remember why?
Is it because the other oxygen is kind of pulling away that electron density? Yeah.
It's actually an opposite situation. Since this is able to contribute via resonance, it's actually donating oxygen in.
Okay.
Yeah. So when you have your aldehyde or ketone, there's only the electron withdrawing effect here. And the only resonance form you can draw is showing electrons moving away from the carbon with the hydrogen. But in an ester, you actually end up donating electron density from this alkyl oxygen. There's no way to push electron density towards it. So that increases your acidity, or increases your pK, decreases your acidity. Okay, so then when we're in between two carbonyls in a dicarbonyl compound, such as a diketone or like a malonic ester, we end up with a much lower pK. And this is because we have two groups pulling away, right? And that also means that we have two different resonance forms that we can draw from our enolates, which I believe we drew out. Maybe I didn't draw them out. but we can real fast. So if we have our enolate from a dicarbonyl, you can push the electron density that way. To create this enolate. And you can also push it back onto the other carbonyl. So there are our 2 resonance forms of our enolate here. 3 resonance forms total, I guess.
I have a question.
Mm-hmm.
On the quiz, you had one that was like in between 3.
Yes. Okay. I can pull up that quiz question real fast. Whoops. Hold on, it's not gonna let me do it while I'm still sharing over here. Sorry, this is gonna take a second. Top Hat doesn't let you open multiple windows very easily. Not when you're in a presentation. Okay. So that would be this question, right?
Yes.
So here, this one has electron density being pulled in 3 different directions. So this is the most acidic proton. So this one wasn't a test of you knowing your pK values. It was you understanding why a hydrogen in between 2 carbonyls is more acidic than one that's next to one, and why it's more acidic than one, or less acidic than one that's in between 3. So this is going to be more acidic because it has multiple resonance forms. You're pulling electron density in multiple directions. And then I think it was Andrea who asked about it. The aldehydic proton would be the least acidic.
Okay, just wanted to make sure.
Mm-hmm. Yeah, that's why I spent so much time last Monday on the why. And then this was kind of a bonus for if you were really paying attention in class, because all of these PKs were given to you in class, and they're in the notes as well, in the videos. Okay, so knowing the why is really, really important. Okay, so last time we were talking about how the strength of the base indicates how much enolate is present. So if your pKa of your base is really, really close to that of the alpha proton, or if the reactants are actually favored in the equilibrium, that means you're going to have very, very little of your enolate present. And the reason that's important is because in chapter 19, that is what we're functioning off of entirely. So chapter 19 is all about situations where you actually have very little enolate present, but you still manage a reaction. So at the beginning of chapter 19, it starts talking about the Claisen condensation. So the key thing about the reactions in chapter 19 is that they all start with a deprotonation of the alpha proton, but very little of it is getting deprotonated. And so you end up reacting, the molecule ends up reacting with itself. So if we have, sorry, let me write this out as a equilibrium. If we add ethoxide to this, we can deprotonate. We'll be in equilibrium. We will have our enolate and ethanol. What is the pK of ethanol again? Yeah. So this proton is about 16. And what's the pK of this proton around?
Like 19 or 20?
No, it's a bit higher for an ester.
25.
25. Okay, so which side of the equilibrium is favored, the products or the reactants?
The product?
It's gonna be the reactants, right? So the side with the least acidic thing. So we are going to favor our reactants. Does that mean that none of this is made?
No.
No.
No, because we're at an equilibrium. It's just we're favoring the reactants. So that means there is a lot more of the ester than there is of the enolate. So the difference between the pKs is about 9. So that means there's around 10 to the 9th of our reactants for every 1 enolate. So the second an enolate is formed, it's going to react with a molecule of the ester. And when it does that, it uses up a molecule of the ester and it uses up a molecule of the enolate. So another enolate has to be formed in order to keep the equilibrium. This is Le Chatelier's principle. So the Claisen condensation is usually written out where you have an ester and your reagents are an alkoxide that matches your ester OR group and the alcohol that matches the ester. Or you might see it as like something like that. So in this mechanism, the first thing that happens is you deprotonate your alpha hydrogen. And you end up with your enolate. So again, we have 1 enolate and 10 to the 9th molecules of the ester. Is it going to be hard for the enolate to find a molecule to react with?
No.
No, it's going to be really easy. One of the teachers that I worked with in grad school used to explain this as he would look at the room, and there were usually about 300 people in there because I went to grad school at a large university. And so there were like 300 undergrads taking OChem too. And he said, if I take this chalkboard eraser and chuck it into the like audience or into the students, my chances of hitting one of you are really, really good because there are so many of you. So it doesn't matter that I only have 1 chalkboard eraser. So it's like you have 1 arrow and many, many targets, right? It doesn't matter how bad you are at archery. If there are, you know, a wall of targets, you're going to hit one, right? So this is going to end up attacking, oh, sorry, let me draw a fresh molecule of the ester. A molecule of the ester. And we are in equilibrium. So now we have our enolate molecule. We have the new bond that we just created. And then we have our other enolate. That was drawn so poorly, I apologize. We have the other enolate molecule that we just attacked, right? What is this going to do next?
Are the electrons going to move and kick something out?
Right. We are going to bring these
It's gonna
electrons
kick
back
off
down.
the
Right.
ester part. Yeah.
Right. And so we end up with a ketone that we just formed here. And keep the color coding.
And your enolate.
Yeah, this is the bond that we made. And then here are the ester molecules from our enolate that we made. So notice this has 1, 2, oh, I somehow erased part of my ester earlier. Sorry about that. We have 1, 1, 2, and then we have 1, 2. So we have the same number of carbons. What we lost was one of the ethoxy groups. So basically we used 2 equivalents of the ester. So if you watch the video, it goes on to explain that at this point, this proton is very, very acidic. So if we have more ethoxide around, Warren, I think I'm answering your question. If we have more ethoxide around, it's going to deprotonate this again because the pK of that proton is very low. And this seems really pointless. So the reason that we end up adding in ethanol or water or something at the end of a Claisen condensation is so that we can protonate that. So that we can literally get back the molecule we just drew a second ago. Because even though this is still a nucleophile, it's not going to be as good of a nucleophile as this enolate. Does anybody know why?
Can you repeat the question?
Yeah, so between these two that are both going to be present in solution, why is this one the better nucleophile?
Are you talking about the stability because it's more stable?
No, this one's actually more stable.
Oh.
Warren, yes, it is a stronger base technically, but that's not exactly why, because there's less of this made. Oh, Samantha got it in the chat.
Yeah.
Sterically, it's better. So same reason as why methoxide is a better nucleophile than T-butoxide, right? T-butoxide is more likely to do elimination because it's bulky. Methoxide is more likely to do substitution. Kind of a similar situation here. This nucleophile is just gonna have a harder time reacting with an ester than the smaller nucleophile. Okay, so that's the general idea.
That's always the case though, right? In terms of like sterics.
What?
Is that something like where it's like always the case where if you have something like that, then it would be more appropriate to go with the less sterically hindered one?
Well, in the case of a Claisen condensation, you're always going to do just one addition.
Okay.
You don't have to worry about using this as a nucleophile.
Okay.
The other reaction that's brought up towards the beginning of chapter 19 is the Dieckmann condensation. That is just a cyclic Claisen. So I'm not going to go through the mechanism here. It's literally just a Claisen with a diester.
Okay.
So one of the key things that's important to note about the Claisen condensation is the setup. It's really, really easy to recognize it. And therefore, when you're doing a multiple choice problem where I'm giving you answer option, it's really, really easy to eliminate the wrong answers. So even if you're a little less confident about the correct answer, you can be confident about what's definitely wrong. So when you see this setup, all right, R prime, it does not matter what's over here unless it's another ester. And then you have RO minus with some sort of metal cation. Usually it's sodium, but it could be potassium. And then you're followed up, or you have alcohol in the same reaction. This is your automatic setup for a Claisen. And you know at this point that you're always going to end up creating a beta keto ester. So notice that this structure here is visible here as well. Actually, I didn't need to circle all those carbons. This is your beta keto ester. So this is your alpha carbon. This is your beta carbon. In the beta position, you have a ketone. So in the Claisen reaction, you are always looking for a beta keto ester answer. One of the really common things that you might see as an answer, let's say this had been a multiple choice problem. I don't know why I drew so many carbons, but you might see one where it's a gamma keto ester. This is not the outcome of a Claisen condensation. So anything that is not a beta keto ester is not a valid answer. So you can go ahead and look at that answer and just cross it off. So you see this setup, you ask yourself, which of these is not even a beta keto ester? And then if there are multiple beta keto esters, pick the correct one. You at least narrow down your choices. Okay, I also want to do a quick introduction to aldol. We're going to do some practice problems on Friday, but I'm also going to bring problems from previous chapters because it'll be our second to last class before the exam. Sarah asked me, do we finish chapter 19 by the end of this week? No, I'm not going to put all of chapter 19 on exam 2. That seems mean. It's just so much of chapter 18 and chapter 19 is interlaced that Top Hat actually combined them into one chapter when they weren't supposed to. It goes hand in hand. So I wanted to talk about it right now. I think I bumped back the reading deadline, but if I didn't, I will for sure. The reading deadline for chapters 18 and 19 will be after the exam. You should still complete your reading for chapter 18 before that. I give you guys later deadlines just because I don't want to force you to get all your work done because I know you have other classes. But please, try and stay on top of your work. That's why the deadlines still do come kind of quickly. And some of your homeworks are actually due at the start of the exam. Samantha, I sent out an announcement about examity dates. Yeah. Okay. Oops. Sorry, my Zoom is being weird. Stop it. There's a bunch of menus open for no reason. Okay. Oh, we're running out of time. So aldol is the exact same idea as Claisen here. It's just with aldehydes and ketones. So you have a ketone and you introduce some sort of base. A lot of times it's kind of a weak base or like a watered down base. So remember the pK of this is around what? Yeah, this is around 19 to 20. And then on the other side, we have our enolate plus water. The pK of water is 15.9. We're going to prefer this side, but there's going to be quite a bit of enolate formed here. So the difference between them is about 3 to 4 units, right? So for every 1 enolate, we have 10 to the 3rd to 10 to the 4th ketones or aldehydes. So it's just another self-reaction. You're going to end up consuming 2 equivalents of your starting material. Now, depending on where you're doing practice problems from, like if you are using outside resources, which is great and wonderful, I hope you guys are finding other places to get help. Make sure that you recognize that even if it doesn't say 2 equivalents, it does not need to say that. It's still going to use 2 equivalents of whatever your starting material is for a Claisen condensation or a Claisen addition, or sorry, aldol addition or condensation. Okay, we are out of time. I cannot hold my office hours at regular time today. Emergency, I have to sub for one of my IAs for 11:42. So I'll be teaching a lab from 12:30 to 3:30. So instead, I'm going to stay on here for about 30 minutes. If anybody wants to stay and ask questions, you can. Otherwise, you are welcome to head out.
I just had a question because I keep confusing myself with different values. Like if there's a negative, pKa can be negative, correct?
Yes, yeah, your very, very strong acids have negative pKas.
Okay. So the lower that the number, so when you're talking about a big number for pKa and acids, are you talking about like the lower number then? Or are you talking about literally like a bigger number? Because I think that's where I get confused is like, okay, I understand that the lower number that you go is going to be the most acidic, but
Right.
then sometimes it's intermixed with like the terminology of like, oh, well, you want to go with a bigger number that's acidic. And so that confuses me.
Oh, okay, I see. Sorry. So like, there are some really big numbers sometimes when we're talking about acidity. What that means is basically these are not good acids, right?
Right.
So like this compound here is not a good acid. It has a very high pKa. You have to have a very strong base to deprotonate it. So when we're looking at our acid-base equilibrium, and we're talking about which side we favor, you always favor the side with the weaker acid because it's going to be less reactive. So it's much more challenging to create the stronger acid than to keep the weaker acid. So when we're doing acid-base equilibrium and I'm asking you which side is favored, we pick the bigger number because
Okay. Yeah, that makes sense. Okay. Thanks.
Yeah, no problem.
I don't really have a question about this stuff, but I was gonna ask if you could just do the alpha condensation. I'd like to see it.
What?
If you could do the next condensation you're doing.
Oh, yes. Sorry, you trailed off there, so I wasn't sure what you said.
Oh, sorry.
So you want to look at aldol, or did you want to look at decon?
Yeah.
Okay.
Whatever you were doing next.
Okay, so aldol, we're not even really going to start. This is not going to be on exam 2, which is why I didn't start pushing on it. Does that change whether you want to do it?
Oh no, yeah, I still want to see it. Like whatever you're about to do.
Okay. Oh, hold on one second. Let me answer a chat. Okay. So for an aldol reaction, do you want me to just do this problem?
Yeah, that's fine.
Cool. So if we're doing an aldol reaction with acetone, I'm going to go ahead and erase this. That's not going to be our product. In the first step, you're going to deprotonate acetone. So you end up with your enolate. Okay. And then like we were just saying, there's going to be a lot more of the ketone left over than the enolate. So the enolate is going to attack another equivalent of the ketone. Here's where color coding can be really helpful. This is the bond that you're making. And then let me find another color. We'll use yellow for our other equivalent. And then this is the other equivalent of the ketone that you just used. Can you see the yellow? Is that visible?
Yeah, I can see it.
Okay, great. So that's just the addition that we've done so far. Does everybody see like where this comes from?
Yes.
Okay. So then at this point, we did make a molecule of water when we deprotonated. And so you end up protonating. And your product here is going to be an alcohol. So you end up with an alcohol in the beta position. So this is what's called the aldol addition product because we added them together. There's another step. Later we'll talk about what causes this, but you can also do an aldol condensation. And an aldol condensation will occur if you take an addition product and heat it up. So if we were to take this beta hydroxy ketone and heat it up, what you end up doing, you still have to have heat also base around as well. What you end up doing is essentially eliminating an equivalent of water. So this becomes just a beta elimination, like E2 essentially. And you end up creating a double bond here and water. So your carbons from your original equivalent of acetone are still there. So this is the direction we're heading. And this is when people start to get really, really lost.
So the 10% of the sodium hydroxide, what is the sodium hydroxide again? Like, why are we using that, I guess?
We just needed a base to protonate.
Okay, so, okay. And then is it the same where you are using, like where did the OH come from? That's just because the hydroxy is what's going to pull off that hydrogen.
Are you talking about here?
In the beginning, when like what you pull the hydrogen off of, is that just because that's, yeah.
That's from the sodium hydroxide. Yeah.
Okay. I just didn't know if it was like part of the reagents because it's right under the arrow. So I just was...
Oh no, I just drew that so I didn't have to try and draw a bunch of lone pairs and a charge right there.
Okay.
Alcohol condensation. Does it matter how much you start off with, like equivalence wise? What that will determine how much water is going to be removed?
So it's one equivalent of water per molecule. So it'll be a 1-to-1 ratio. So 1-to-1. Is that your question?
Yeah, well, yeah, sort of, because like in lab they had the aldol condensation and it came out in 2 equivalents, but that's probably because we did 2 equivalents of the aldehyde, so that makes sense.
Well, no, so if you start off up here, starting with just your aldehyde or your ketone, yeah, you'll end up with 2 equivalents. Down here, we've only made 1 because we would have made 1 up here as well. But you also use it.
So then wait, what was the difference then? Because you said we made 2 up there, but 1 down here.
So if you drew
pointing to the screen like you can see me. Sorry.
If you drew out the reaction as sodium hydroxide and heat all in one go.
Mm-hmm.
You're saying this is where they had 2 equivalents of water?
No, no. It was just in lab because there was 2 equivalents of an aldehyde.
Right, so that's what I was saying earlier when I drew out these problems, is that you do use 2 equivalents, but it doesn't have to be indicated by the problem.
Oh.
Because it's your job as an OChem 2 student to recognize that only part of this is going to get deprotonated at a time. And so you end up using 2 equivalents.
So it is safe to assume that, like, unless it says specifically 1 equivalent, that there's going to be more of it in there.
Right. So if you are drawing out an actual balanced equation, then we would have to put a 2 here.
Oh, okay.
But if I'm giving you guys a problem to complete, I'm just going to write it out like this.
The basic structures. Okay.
And you are supposed to know that this is your product and that it uses 2 equivalents. Whoops. Circled the wrong thing. That it uses 2 equivalents.
Yeah. So, because in the equation in the lab, it did have, like, we had 2 equivalents of the aldehyde, but then 2 equivalents of water came out.
Yes, that's because they're giving you the balanced equation.
Okay, I see what you're saying though, but it's still a 1-to-1 ratio.
Yes.
Oh, cool.
So yeah, you're only eliminating 1 equivalent of water. Any water that you made in this previous step gets used up. So I'm not sure why they're saying 2 equivalents of water. That's not what I would say.
Yeah, that's why I asked. Okay, thank you.
I have a question. So could you do that, like, with the product that you just formed, could you do this again on the other side of the ketone?
You mean like take this and further react it?
Yeah.
Isn't that the... Oh no, that's not directly on the carbon. Never mind.
I mean, I guess so. Yeah, not normally.
Okay.
Usually once you introduce things to this is called an alpha beta unsaturated ketone. So, oops, oh my God, I was trying to write alpha and I wrote an and. Okay, alpha beta unsaturated. You're gonna hear unsaturated carbonyl over and over and over when we get to this next chapter. Usually when you add something new to this, it's going to add either in the alpha or beta position on its strength as a nucleophile. So if you added hydroxide here, it's going to act as a nucleophile. It's going to add in either the alpha or beta position. And we'll talk about like which one goes where later, but yeah, it's going to go through that route instead of doing a deprotonation or something.
Right. Makes sense. I was just curious looking at it.
Is that kind of like how the polymers are, like in polymerization? Like, you know how, like, because it like repeats and things like that?
Yeah, so in aldol, you end up stopping at the dimer, essentially. So just 2 units. Polymer chemistry usually uses easier chemistry. There aren't a lot of polymers that would be made through aldol.
Oh, I see. Yeah. Okay.
So for this exam, are we stopping after the Claisen condensation, or do we need to know like the crossed Claisen condensation?
So Claisen and Diekmann and crossed are all together in my mind. Crossed just means that you have 2 different esters, and usually that is limited by the presence of only 1 alpha proton. So usually that's something like ethyl benzoate, where there are no alpha protons present, and you react it with, say, like ethyl acetate, which only has 1 type of alpha proton. So when you add in ethoxide into this situation, the only thing it can deprotonate is here. And therefore, this is going to be the only thing that makes, sorry, what's the word I'm looking for? An enolate. And then this is the only target. So you would end up exclusively, I don't know why I'm drawing this over here. It's the product of this reaction. Here's your new bond. You would end up exclusively with the addition of ethyl acetate to the ethyl benzoate.
Okay, thank you.
Yeah, so that's really not any more challenging. A lot of people find it actually easier to see these products because you don't have to, I'm trying to scroll. Okay, there it goes. You don't have to look at the problem and just know that you're using two equivalents. A lot of times when I give a Claisen condensation, people will draw stuff like this as their answer because they don't know what to do with it. So they draw like a hemiacetal. But when I give this, they're like, oh yeah, this is gonna react with this, and they figure it out.
And then what did you say the one was with the rings? Like, I guess just...
Yeah, the Diekmann condensation is a Claisen condensation with a diester.
Oh.
Yeah. So you have two alpha carbons here. They are equivalent to each other. Only one can get deprotonated at a time. And then it's going to end up attacking itself. Sorry, and the conditions would be...
Would that be a 5-member ring then? No, 6.
Yes. No, you're right, because it'd be one.
Because then the other part's going to be hanging off, right? Okay.
Right. So this is another example of numbering your carbons first. Like these are going to be in the ring because this is attacking over here. Draw out your ring and then number them. So you're still going to have, I don't know why I changed my color, sorry. You're still going to have a carbonyl on 5. And then off of number 1, you're going to have your ester. And then always, always, always check yourself. Alpha, beta. This is a beta keto ester. I give this type of question all the time, and I'll draw the wrong size rings as options, but then I also give like this as an option. So alpha, beta, gamma, wrong.
Oh, I see.
We're not going to be required to draw like how we have to draw in the extra credit because that extra credit drawing is so frustrating, right? I can't draw any, like I want to draw the thing that's in my mind or on my paper and it won't, like I can never figure it out. And it's really
that's why it's extra credit, is because that's still a pretty new tool to Top Hat, and so I didn't want that to actually be part of your grade.
Yeah, I was like, this is taking me just hours just to finagle what I want it to look like.
Yeah, there is a lot of value to them just because coming up with the answers on your own is really, really important versus doing multiple choice. So like students who only do multiple choice problems are going to struggle so much with the final exam, even though it's multiple choice. So doing some handwritten problems or some written problems in general is much better practice.
So for the, I'm sorry, I have a question.
No,
so
go ahead. Go ahead.
Where you attacked the other carbonyl to form your ring, what is the extra carbon like hanging off? Like, is that not somewhere? Or am I like not seeing it?
This part is this right here.
No, on the other side. I guess like the left side of the.
So where is this carbon?
Oh, I'm so stupid.
No, you're not
Okay,
stupid.
ignore me.
That way you were looking
I
at-
low key was not even paying attention, and I did not even see that the other part of the Esther.
Okay. Yeah, that doesn't make you stupid. That makes
Yeah.
you new to this, and that's fine.
Are we gonna need to know a lot about like polymers and like the
No,
steps?
no.
Yeah, that section was not good for me. That was a lot though,
They
but
talked about it so much in like the module reading, and it was a lot.
Yeah, I know. The modules, they are, it's not a perfect book. So the Top Hat book was originally very, very different from what the rest of the department uses. And so we rearranged it to look like the Solomon's textbook, but we have not yet had the time to go through and remove extraneous information.
yeah, 'cause there's a lot of the stuff. Like all of chapter 17 was a really big, thick part, but then it confused me because you know how you said like make sure this section is like sectioned off and separate from what you've already learned from previous sections. And I tried to do that, but then like reading through it, I could get through the majority of it, but then like it really did confuse me. So, but when I went to reread everything from like the previous carbonyl section, it was literally just repetitive. It was like having that section stuck with chapter 17 in it too.
Yeah, the reaction
It was so
conditions
much.
are all very similar. Like you do a lot of the same things, but the outcomes are very different. And so that's all I mean about like drawing the hard line in your head is like before you answer a problem, go, okay, this is a ketone. It's going to do an addition. I don't have any leaving group to kick out. Or you look at it and you say it's an ester. I'm going to do an addition, but then I'm going to eliminate something. So like you just have to make that decision before you answer the problem. That's all I meant by that is like you have to know in your head that those two types of things, aldehydes and ketones versus carboxylic acids and their derivatives, have very different reactivity. So even though like they go
because
through,
they're more easily reactive, right?
Yeah, so aldehydes and ketones are very reactive. It depends on the conditions that you're looking at, but for the most part, aldehydes and ketones are more reactive than carboxylic acid derivatives, except for like the acyl chlorides and anhydrides are very, very reactive.
Okay, yeah, because that's where I was like, where do I put this in my plethora of knowledge of all these things?
You should never have to compare them.
Okay.
Yeah.
Okay.
Yeah, that should not be a competition.
Okay. Yeah. Because that section, like I was just very confused.
Yeah, that's valid. It's a lot of information. OChem 2, like for some people, OChem 2 is easier because it's just reactions. It's not as conceptual as OChem 1, like learning stereochemistry and stuff. And then for others, OChem 2 is like, there are so many reactions and it's a lot to keep straight. Yeah, I was definitely more of the latter party. I thought OChem 2 was so much more fun and so much more interesting. But it's a lot to keep up with and you have to do a lot of practice problems and it really does take a lot of time.
It does. Yeah. Cause trying to remember all of them. Cause I'll go through all the stuff and like with like the quizzes, I'll go through and I'm like, yeah, this will happen. But then I'll forget like the minor thing that you're testing on. And then that's what makes it all wrong.
Yeah. So definitely try to avoid looking at things like exceptions because there really are no exceptions in OChem. Like sometimes they're taught like very specific rules, but they're not. It's like you either understand the pKa's and the relative reactivities or you don't. Like most of OChem comes down to pKa. So when we say like the exception here is this, it's because it's a pKa thing usually. Or it's a steric thing. So like knowing the general rules of OChem keeps you from having to think about exceptions and getting tripped up by them.
Yeah, because I was taught that there was like, here's all these rules and I have like papers of just rules and like steps of how to go about with answering, like when we're doing like when you get to the PK, like this whole chapter, and with all like the acid base stuff, I was taught to just look at like the molecule and say, okay, where are you at? Where is this a reaction going to take place? And then what type of reaction is it going to take place? And based off that, there's like all those rules, you know? And so I wasn't sure if that still applied now that, but I don't know.
No, that definitely still applies. It's just all those rules come out of the same concepts.
Okay.
Yeah. So yeah, I think different people teach OCHEM differently. Usually people whose degrees are directly in OCHEM, like mine, were like, oh, OCHEM is so wonderful and conceptual, and if you understand the grand plan, then you're great. Like that's how we approach OCHEM because it's what we studied, and like I see a big picture now. And then people who didn't study OCHEM specifically, like for their PhD, tend to be like, memorize OCHEM, or, or here's a list of rules that you can follow. So like, yeah, the teaching styles tend to vary depending on like where your passion is, I think. And I love OCHEM.
Yeah, well, I mean, I really enjoyed it. It's just like you said, it is a lot, and so trying to keep it all straight is what's practice, needed practice. But
I've definitely enjoyed 2 more than 1. I've definitely enjoyed OCHEM 2 way more than OCHEM 1.
Yeah, I think it's more fun because you know so much, right? It's really cool.
I feel like stuff from OCHEM 1 is starting to make like a little more sense now. I guess now that
there's a lot of conceptual
like,
stuff I was
that's
given.
what it
Yeah.
was.
Yeah, same. I feel the same.
That's awesome. That's how it should feel.
Well, because I like right now, like everything that's like, wait a minute, I've seen this before. I'll go back, and I've been studying a lot of like going back and restudying my OCHEM 1 and realizing, oh, that makes complete sense now. Or I could like read this whole paragraph and not have to look up a single word.
Sometimes I look at my old exams from when I took OCHEM in undergrad, and I'm like, how did I get that wrong? I was such a doofus. Like, it's so obvious now. Yeah, it always feels that way, I think.
Yeah, so I was wondering, like, did we need to come to office hours to review our old exam? Because I find that does help me in terms of like where I went wrong in my thinking, because also with Top Hat, like I struggled with like them marking a lot of my questions like in the in-text and in the homework correct, and saying that what I did was correct, but then when it showed up on the quiz, I would answer it the way that I thought was correct, and then it would all be wrong. And then they're like, when I asked them about it, they're like, oh, well, the algorithm's correct. It just might be a glitch in the screen on like what you're seeing. And I'm like, that doesn't help. That's not helping me.
Well, there is actually, I've made this complaint a couple times this semester because people were sending me screenshots of their correct answers.
It will be like literally green. Yeah. And then, but then
like it'll be marked, it'll be marked red, but then it says it's correct.
Yes, that just happened recently too with with this last chapter too. There was like you could mark one green and then one in red, but it would say correct when it really just wanted one answer.
Yeah, they're stumped, and I've expressed my displeasure, but your grades are correctly represented in the grade book, and that's what really matters. I know it's frustrating, but like I've told them, like, my students are sending me emails and they're asking me, why was this marked wrong? And I'm like, well, because it is wrong. But then it's green and it says it's wrong. I'm like, well, it's not because it is wrong. Or the wrong answer is marked correct. Those are easier for them to fix. But yeah, for some reason there's a glitch in like what actually ends up being shown to you. And that's the worst because it's so confusing. And
yeah, it's so hard. Like, I don't mind if I'm wrong. I actually learn more when it's like, you're wrong because of this, not correct, move on, but now you're wrong again. Because yeah, like you said, it's frustrating because so that I was just wondering if that was a possibility to go over that or not.
Yeah, I originally hadn't released your exams back because it took me a really long time to write it all up, but I usually hand back exams in my in-person class, so I'll just release it to you guys.
Okay.
Yeah.
Thank you. And then for like the reviews that are already up right now, is it still okay to like go through those, like to review for?
Yeah, like those are just practice problems. I kind of wish I hadn't labeled them as exam review because some students were really upset that it didn't match the exam exactly. But those are questions from a test bank, and I don't teach you guys using that kind of terminology necessarily.
Exactly.
So I try to write my questions the way that I talk to you so that they make more sense.
Right.
And so I don't know, a lot of students felt like the questions were very different, but Anne and I felt like the questions were the same topics and the same ideas.
No, they were, because I went through a lot of the first one, because Anne went through those too, and it helped because like in her ISI session, she was able to explain why an answer would be over another answer, which definitely helped in like trying to clear out any other questions. But yeah. In comparison to the exam, I'm yeah. Maybe it was just because like the idea of like, well, we only have 50 minutes and then there's like test anxiety.
Yeah, the exam was very long, and yeah, I tried to explain that to you guys. Like I just had to make it long because it really did cut down on how much made it onto CHEG.
Okay.
Yeah, and so that's why like I also put a curve on there. I don't usually curve and give extra credit. Like I let you guys earn points back, but I expected this average to be a good 10 points lower just because of how long it was. So I gave you guys those points back.
Oh, okay. Yeah, that helped.
So yeah, it wasn't like I wasn't trying to punish you guys. I just made it long so that I didn't have to worry about as much ending up on CHEG. Because last semester, like my entire exam would appear on CHEG. And that was very frustrating because then like the students who had CHEG accounts were doing really well and the students who didn't were struggling or like getting, normal grades. And
yeah,
that's not right to me. So writing a long exam is one of the best ways to eliminate that. And so I just gave you guys some of those points back because I'm not trying to punish you. I'm just trying to make it fair.
So. Okay. Yeah. I think a lot of people too are asking in the chat before everybody left if there was still a Zoom option this time.
Yes, there is. Yeah, it's the same testing protocol as before.
So it'll be the Wednesday, right?
Yeah.
Okay.
So I still prefer that people take it on Examity, but some people have like incompatible computers and stuff. So if your computer is incompatible with Examity, obviously you can't do Examity. Like people who have Chromebooks, like you just straight up cannot do Examity on a Chromebook.
Oh yeah. Okay.
Yeah.
Okay, well, cool. Thank you. Yeah, I haven't been able to come to office hours either because of, life. But is it okay that I email if I do have a question? Like I email my questions like as a list or something, and then I mark it like questions help or something.
Yeah, no, that's perfectly fine. I'll answer you as soon as I can. Just on Mondays I work at school from 8 a.m. to about 10 p.m. because I have
You're doing all the other classes, yeah.
Well, no, the stock room. There has to be a faculty member on campus, and on Monday night, that's me.
Okay.
I will be in the stock room, and so sometimes I have time to answer email while I'm in there, and sometimes I don't. So
okay.
Just depends on how busy the stock room is.
Okay. Okay.
I can answer things the rest of the week, like Tuesday through Friday. You'll definitely get a quick answer. Saturday and Sunday, I try to turn off my brain a little bit.
Okay.
Down on email just a little bit.
Okay. Yeah, because I like going through a lot of it, I'll just be like, oh, what's this question? But then during class, I feel real dumb if I try to ask or you answer it, so I don't need to ask like in the middle of lecture.
Well, if you have a question and you don't feel dumb, like ask the question because I guarantee you there's at least like a handful of students.
I feel like a lot of them are so basic or maybe not relevant to the material, but because a lot of the questions that I have, like I said, they stem from me reviewing older material and trying to tie it back in to what we're doing now and trying to make that those distinctions and things like that,
Yeah, I think that's great. No, I've never listened to a question from you and been like, that's a stupid question. I've never thought that. Usually if somebody asks a question and I feel like I already covered that, I'm like, okay, so I didn't cover it well enough, or like I need to rephrase how I said it. So yeah, asking those questions is helpful to me because then I know what's not working.
Okay. Okay. Thank you. Yeah, because I'm always like, oh, I don't know if I should ask that. Okay. Thank you.
I don't want you guys to be scared of asking me questions. I want to answer your questions.
Because then even in the groups, like when we do groups, I don't mind getting in there and talking and things like that and throwing out what I think is going to happen, but half the time it's wrong. So then it's corrected, like, oh, okay, I see what I did wrong there. But I always am worried, like, oh, everybody else is gonna be like, oh, this person told us this is gonna happen, but it didn't. You know what I mean? So I don't know. I mean, it's beneficial for me because then I can learn, but I don't know about everybody else who's just kind of like, yeah, that sounds good.
No, usually if you ask a question, even if nobody else had that question, they'll be like, oh yeah, that is a question and I did not understand that. And yeah, I'd rather you guys ask me a million questions and slow down lecture than sit there confused. That's not helpful to anybody.
Oh yeah, because I that's what I'm worried about too, because I know there's a lot of material and don't want to like hold you back because there's only like X amount of time.
Yeah.
And so
I mean, that's why like the videos are great, is because like we have that, you know, normally we don't get to work this many problems in class. So like this is kind of actually a really nice format because you can watch the videos at your pace. You can rewatch them as many times as you want. And then in class, we mostly work problems, which I don't usually get to do with you guys.
okay. Well, thank you very much.
No problem.
All right, bye.
Bye. See you later. Erin, did you have a question? Nope.